Ethereum being like its own kind of standalone blockchain, but eventually having this goal of enabling scalability through layer 2s. The basic idea of kind of what PeerDAS is going to end up doing, column sampling. But this is, again, very abstract. The gossip protocol is not built for gossiping a lot of data. And yeah, I think it's fine when you're not like pushing the limit of basically bandwidth that nodes can use. But once you start pushing against that, you really kind of hit a barrier there. And I think we're kind of moving away from that. Like, I think PeerDAS really is like a pretty big step forward. If there's anything that looks like a security problem, then, well, that's like priority number one for Ethereum. Like, there's never...
Welcome back to PEEPanEIP, the one and only EIP series where we explore Ethereum proposals for upgrades and those making an impact across the Ethereum ecosystem. This is episode 156, brought to you by ECH Institute. I'm your host Pooja Ranjan, joined today by my colleague Akash from Multimedia Team. Today we are diving into something that could support how Layer 2 operates. EIP-7594, PeerDAS, also known as Peer Data Availability Sampling, is a very wonderful proposal to talk about this. Documented in January 2024, this is a standard track core EIP in last call status and scheduled for inclusion stage for Fusaka upgrade. If you ever have used an Layer 2 project and wondered why fees aren't even lower yet, or why Ethereum still struggles to scale data, perhaps PeerDAS might be an answer, or at least one of the answers that we are looking for. So to unpack all this, we are joined by someone who is deep into the design and research and also one of the co-authors of EIP-7594, Francesco D'Amato. Welcome, Francesco.
Thank you very much, and thanks for having me.
Francesco, your X profile suggests that you are a researcher dealing with wacky protocols and weird acronyms. We'd love to know you more. Maybe a brief introduction, please.
Yeah, actually, the Twitter bio is pretty accurate. I mean, PeerDAS is one of these weird protocols, but yeah, I joined the EF 4 years ago, and I've been in the research team since. And I've kind of hopped between, I want to say, most of the consensus layer research problems at this point, and some also like beyond the consensus layer. I think more or less I've been involved in like protocol design, like broadly. But yeah, over time I've sort of drifted a bit more into being a bit closer to the protocol, like not so much in the pure research stage, but also a bit in the maybe specification stage. And yeah, and also just generally like paying more attention to the actually, getting an EIP to mainnet part of the R&D pipeline. And so that's kind of how I got to PeerDAS. Like at first I was just, interested in what the other people in the research team that were a bit more closer to the actual protocol, what they were doing with this. And yeah, kind of got interested with some colleagues, started thinking about it. And eventually it, ended up kind of working on it in a much more like hands-on sort of capacity. And yeah, that's where I'm at now. Like a lot of, I guess, my time is spent thinking about like, where do we go from here? We have this like upcoming upgrade, but yeah, what's next essentially for the DA layer? But then also just more generally kind of, yeah, still like protocol design and thinking just in general, like how do we want to evolve Ethereum in the future?
That's pretty interesting background and the work that you are doing around. I understand this is not your first proposal. For listeners who may not have followed it before, I'm happy to share that Francesco had been on the show before and had discussed about a proposal which unfortunately could not make it to the upgrade, but good that we are having him again to talk about a proposal which is going to be in Fusaka upgrade. Now the proposal in last call, so I'm hoping it's gonna make it. Thank you so much for sharing about yourself, Francesco. Without further ado, let's peep into the proposal.
Sure. Yeah, so as I said, PeerDAS, it's EIP-7594. But actually, before we get into that, it's worth taking a step back and maybe just having a refresher of EIP-4844, which is kind of how we got here in the first place. Most of you probably are familiar with this, but yeah, more or less, we have this overall story of Ethereum being like its own kind of standalone blockchain, but eventually having this goal of enabling scalability through layer 2s. And this sort of needing a lot of data to enable basically these layer 2s to post transactions on Ethereum. So in this case, here, these like red and blue transactions are meant to be Could be Arbitrum, could be Optimism, could be Starknet, some layer 2 that's essentially just putting its transactions on Ethereum and not having Ethereum actually execute them to achieve like basically greater scalability than if the chain had to execute everything. So yeah, this data needs to sort of be on Ethereum to get the maximum security that you can get from this kind of construction. And as of last year, now I guess a year and a half ago or something, with EIP 7494, we've had this quite like big unlock in scalability of this construction, because we've added this sort of like what looks to be here like external data that's sort of outside of blocks. This is what we call blobs. And they've basically expanded the capacity of the Ethereum data layer by quite a lot. Initially about 3x, and then now further like 2x in the last upgrade in Pectra. But they've also kind of set the stage for what's to come. They've kind of really, in a way, created the Ethereum data layer as a separate product. Before Rollups used call data, but it was more of like a hack in a way. So yeah, specifically what two main things that 4844 has done, it has created blobs as a resource. And in particular as a resource which has its own independent fee market. So it's somewhat separated from L1 execution in particular, which call data like wasn't really. And so yeah, this is like quite important. It's somehow, these are not competing with L1 transactions. Essentially, they have their own kind of capacity and price. And then they're also like stored and served only for a fixed amount of time, like 18 days. So in particular, they don't kind of keep bloating nodes. Like nodes only have to keep a certain amount of disk storage for these blobs, and it doesn't grow forever essentially. And so this is on the good side, like the sort of good things that 4844 has given us. Plus it has set, as I said, set the stage in particular in terms of the cryptography for what's to come. But there's also the bad part, which is nodes are still downloading all of the data. So this like red blob, blue blob, and so on. Every node has to download all of it. Then sure, eventually they can forget about them, but in the meantime they have to download all of it. So it uses like as much bandwidth as sort of the whole amount of data requires. And so that's the part that kind of we want to still address. And that's where data availability sampling comes in. So data availability sampling, again, right now we're not talking about PeerDAS purely, but more just as a general technique, but it's worth, I think, going through it in this way. It's just this like, general idea that you can take some amount of data. In this case, it's this blue part. This could be any data. You can think of it as whatever kind of arbitrary bytes, and it's split up in some way. And then you can basically introduce redundancy in it. So this orange part, which basically makes it so any half of the data allows you to reconstruct the whole data. So it's just introducing this kind of extra information that lets the data be reconstructed from any sufficiently large part of it. And this turns out to be like a quite powerful thing for the problem that we have, which is we don't want nodes to download the whole data, but we still want to keep the same security guarantees that we have before. And what it gives us is that basically to check that whether a blob is available, you only need to make sure that 50% of it is available, not the whole blob. And now this is where kind of sampling comes in. Once you have this 50% property, it's something that you can essentially just sample. Like you can just keep trying, and it gives you like a better and better. The more samples you get, the kind of lower of a failure probability you have. So yeah, basically what we ideally want is this, that a node doesn't have to download everything. It doesn't have to download the whole blue part or the whole blue or the whole orange part, or even any 50% of the data. It just has to download like a few chosen kind of pieces that it randomly chooses, and the number of these can be constant. It doesn't have to be scale with the size of the data or something like that. And so yeah, basically it really should be like a small portion of the data. And what does this look like if we have, so I mean, yeah, this you can think of as an actual blob, like an Ethereum blob. Maybe the blue part is a blob and the orange part is this extra information. And so the whole thing is this like extended blob. But then what do we do if we have a lot of blobs? There's multiple things you can do, but one thing you can do that to sort of trivially extend the base construction to having multiple blobs is that you just stack them up on top of each other, and then you do the same sampling for each. So right now, instead of sampling one piece for each blob, you basically sample like a whole column from this whole kind of matrix that you obtain by putting all the blobs on top of each other. And this is the same thing that if you were to sample each blob individually, like here you just, for each blob, you're just choosing some pieces to get, but you just always choose the same indices so for each row, you're choosing the same index. And so you end up with sampling columns. And so, yeah, that's the basic idea of kind of what PeerDAS is going to end up doing, column sampling. But this is, again, very abstract. Protocol is much more like concrete than that. So question is like, okay, how do you take this abstract idea and actually put it in the protocol in a way that guarantees all the security properties that we have? And how do you think about how do you actually get the data, networking, and all these things? And there's more than this, but like these are maybe the three most important high-level parts that we can think of, that we get when we actually concretely think of trying to put sampling into the protocol and to make use of it. The first one is distribution. So we have some proposer or builder, like whoever is actually making a block, and it's going to contain L1 transactions and L2 transactions and all of this. And so these blobs kind of on the side, how does it actually get the data to the network in the first place? Like somehow this data has to go from this source to people that basically eventually want to sample it. Then once the data kind of exists in the network, some nodes actually want to sample like specific parts of it. They don't want to download like the whole data. They just want to get, maybe these columns here, and each node is going to have their own kind of choice. And so how does this process actually happen? And then reconstruction, which is, so we have this idea that, okay, in principle, 50% of the data is enough because it can be reconstructed, but it's not enough that it can be reconstructed. It needs to be reconstructed if the case arises that it's actually not fully available. So if you have, 51% of the data, you actually eventually want to go to having 100% of the data. So you want to go, from this sick kind of network where these columns are missing. And sure, like there's not that many that are missing, so overall everything is still reconstructible, but you still want to actually do the process of reconstructing to end up here in this like nice, healthy network with everything being available. So these are at a high level like the main phases that we want to try to somehow construct in the actual protocol. And that's where EIP-7594, PeerDAS, comes in. It actually says, how exactly you should do all these things. And the first simplification is that it's doing distribution and sampling as one process. So it's not thinking about, okay, somehow disseminating the data to the network, like in whatever way, and then nodes are going to do sampling once the data already exists from in the network. Distribution and sampling are essentially one and the same. And how does this work? Well, nodes want columns. Ultimately, this is the thing that they are trying to sample. And so this is exactly how the data is distributed. On a network level, there's basically these like column subnets, this like sub network that you only participate in if you want a specific column. So, maybe this network you only participate in if you want the first column, and this is for the last column and so on. And so this is only going to contain some nodes, the ones that actually care about that column, because that's the one that they're sampling. And so essentially, we kind of split up nodes in these sort of sub-networks, and then columns get pushed into these networks. So the proposer will send this one to the first one, this one to the last one, and so on. And nodes gossip around as they usually do in these kind of gossip topics. Meanwhile, the block is being sent to everyone in the same way, exactly the same kind of gossip process, which is you send the block to like a few of your peers, then they send it to a few of their peers, and so on. But this happens with all the nodes, and this happens just with the nodes that are interested in those specific things. And so eventually testers, but also full nodes will end up basically getting this block, and then the columns that they're actually sampling. So whichever things they're interested in, they only get those. And so that's distribution and sampling basically as one process. And then how does reconstruction work? At this stage, it works with this one of n honesty assumption, which is essentially that there has to exist at least one node in the network that's actually participating in all of these instead of just some. So there has to be some node in the network that's not actually doing just sampling, but that's fully kind of interested in the whole data. This could be, for example, an optimism node that is interested in being able to always recover the data so that it can participate in the fraud-proof game. Or it could be, someone that's running a node. It could be Danny Ryan running a node in his basement. It could be anyone, really. It could be altruistic. And actually, there's mechanisms in the protocol to make this not just coming from altruism, but as a baseline assumption, it's still like a pretty weak assumption like that. We don't really necessarily need to incentivize to be quite sure that there's someone out there that's doing this, because also it's not particularly expensive to do. So there's this assumption that someone would do this. And if they do, then how do we go from the sick network to the healthy network? Quite simply, there is this node. Again, it could be Danny's node in his basement. It gets all the columns. It does the reconstruction locally, and then it just reseeds everything to all the topics. So, maybe this was a sick topic that was missing a piece of data. And then this node would kind of reseed the data in the topic where it's missing. And concretely, how much data are nodes getting? Like what does sampling concretely look like kind of numerically? Well, nodes basically have to, for security reasons that we don't really have time to go into too deeply, have to participate in at least 8 of the 128 column subnets. So there's 128 of these vertical subdivisions, like columns, and you have to sample at least 8 of them. at this stage. I mean, in this first version of PeerDAS. And so what does that mean is that you're downloading 1/16 of all columns, and that's 1/8 of the original data, because we have kind of the original data is this blue part, but then it's doubled into this with this orange kind of redundancy part. And so if we were to just think about this, we basically could support 8x more blobs essentially, because at least the weaker nodes, they only need to do 1/8 of the work in terms of the bandwidth and storage. Now, of course, this is not the only thing that matters. There's more aspects than just sampling. Like the whole system is more complicated than just this one kind of parameter. But at a first approximation, that still tells us like something useful. But yeah, speaking of the whole system, it's actually worth like zooming out a bit and not thinking just about, so we've kind of been thinking about just this final part of having a proposer and sending out the data. But the whole system, as I said, it's more complex, and it's worth like taking a look at it. So as usual, we have Ethereum, we have these like two big components of the protocol, the execution layer and the consensus layer. And on the execution layer, so far we haven't talked about it at all, but the main contribution of the execution layer the main relevance of the execution layer to this EIP and in general to the data layer is the mempool. So we have this blob mempool where basically someone that wants to make a transaction, like for example, this could be like a optimism geth node that wants to send its transaction to the network. It might choose to do it through the mempool. And so, yeah, it would send it and it would come with a blob with it. And then eventually all of these blobs get taken by some proposer, some EL node through the engine API, which is this basically API that links the EL to the CL. So it sort of allows us to cross this barrier. They would end up at a CL node of the same kind of entity. And then we go back to the process that we had before. Like at this point, okay, these blobs have been turned into this whole matrix with this extension and like this, breaking them into columns. And then we basically publish them in the same way that we discussed before. And eventually they end up to a tester, they vote, we finalize, and all the kind of things that we know on the CL. And yeah, I mean, basically what is happening here, but I mean, somehow block building is touches everything. So how you get transactions from the mempool, what exactly are you doing here, how are you doing this publishing, like block building is somehow like really the key pipeline in all of this. And so it's worth like basically zooming into this and what are the challenges there. So yeah, to build a block, you need to be able to do a few things in a timely way. You need to be able to run a mempool, first of all. Somehow you have to get these transactions from somewhere. And you have to be able to compute KZG proofs. We haven't touched on this and like what even this means. It's part of this kind of cryptographic magic that happens in the protocol, but I'll mention basically what's happening with this. And then you have to be able to do this initial distribution of columns. So when you are kind of pushing the columns to the network, you have to be able to do that fast enough. So first, for the mempool part, something that you might notice is at this point, we've basically discussed, let's maybe go back to the picture. We've, this is the mempool, this is this kind of CL distribution part. This is where we've mentioned columns, where we mentioned sampling. So we have this like red kind of samples. Here, there's nothing like this. Here, we just see blobs. There's no columns, there's no sampling. And so the immediate question is, doesn't this kind of defeat the whole point of the construction? Like if we've introduced sampling on the right, but all the blobs still exist on the left and there's no sampling. What is the point of that? And so actually, it seems counterintuitive, but there is still a point, and basically the reason is that the CL, and in particular this kind of critical path of actually pushing the blob data to the network, is much more of a bottleneck basically than this kind of mempool part that's happening on the EL. And this is for essentially two reasons. One reason is that there is no strict deadline for propagating things in the mempool. So propagation, you send a transaction to the mempool. Of course, it's great if it propagates fast. It makes your transaction end up on chain faster, but nothing breaks if the transaction takes 10 seconds to propagate, even 20 seconds to propagate, or really however long. In principle, sure, it's maybe bad user experience if it takes too long, but that's about it. The protocol is not going to break. We're not going to be missing slots. There's not really going to be like any evidence that something has gone wrong, other than maybe like some rollup out there being a bit upset that the transaction took a bit longer than it should, which is important, but much less important than missed votes and all these other consequences. So here we can use basically 12 seconds of every slot. Like the whole time in principle is open for propagation. And here we cannot. There's only a very kind of brief part of the slot, which is at most 4 seconds, which can be used for this propagation thing. So everything is basically much tighter. The other thing is that on the EL, blobs are propagated by what might call announce and pull. So you basically tell your neighbor, here's a blob, do you want it? And then they maybe say yes or no. And what this implies is that nodes never download things twice, because once you have it, you always say no. And so you're never going to waste bandwidth downloading something that you already have. And I mean, this implies that there's this kind of announcing part, which adds a bit of latency because you need to like announce and then get a response before you send anything. But it also means that there's no duplication, like you never waste bandwidth basically. On the CL, and partially because we have less time, so everything is a bit more kind of in this tighter window, we don't do this on the CL. You propagate by push, so you don't say I have a blob or I have a column, you just send the column directly. And this actually ends up in a lot of duplicates and so a lot of wasted bandwidth. And I mean, this could be improved in the future, and I think should, but that's not how it is today. And that's how it works for everything in the CL in general. It's not like a feature specifically of columns. So this means that with a combination of these two things, the EL is essentially much more efficient in propagating blobs than the CL. So the CL is it's much more important to first start having sampling on the CL than it is on the EL. Basically, the EL has a lot of slack for now. Then there's this second component that I mentioned, which is cell KZG proof computation. And yeah, maybe we have to take a step back and first say what even is a KZG proof, what is a cell KZG proof. So we have a blob, or in this case, a column. A column is split up in cells. Each one is coming from a specific blob. But then it has associated to it a KZG commitment, which is this like little thing next to it. It's a cryptographic commitment to the whole blob, and a proof. And so yeah, this basically we have KZG commitments, we have KZG proofs for each cell. And what this proof does is it allows you to prove that this cell is actually the right cell for this commitment at this index. So without having the whole blob. So given this commitment, the proof and the cell, you can be sure that the cell is actually the right thing, the right piece of data that's supposed to be there, which is very important when you're sampling, because let's say you sample this cell and this cell. Since you don't have the rest, it's very important that you can tell that, okay, still, this is the thing that I was supposed to get. This does correspond to the commitment to this piece of data. So this, in a way, like it's what you might do with a Merkle proof in another context, that you don't have the whole data, but you still can figure out that this piece of data is part of this whole that I have a commitment for, like a Merkle root in that case. But this is kind of using different kinds of cryptography that's more efficient for this case. But still, basically same idea. And basically a column comes with all of these proofs and all of these commitments so that you can verify that the column that you're supposed to get, essentially, that you're not being tricked into taking a thing that looks like a sample but isn't actually the right sample. And when you build a block, you need to compute all of the KZG proofs for every cell, which is a lot of cells. It's like 128 cells per blob, so it adds up. And proof computation is quite slow. So for a single blob, it takes this much, like about 200 milliseconds, let's say. Whereas proof verification, I mean, as usual, there's this kind of asymmetry between computation and verification. Verification is always faster. And in this case, it's maybe, I think, like 10x faster or something like that. It's much faster. It can be batched across the column. And so it's somehow much better if this computation is not being done. Well, for one thing, it's not being done over and over again, but also it's not done in the wrong parts of the slot. It's not done in the critical path in particular. So this is what a design might have looked like, where proof computation happens right here. So these blobs come through the mempool. Then you decide that you actually want to kind of include them in your block. You create this matrix, and this matrix has to come with all the proofs. So it's actually here, there's one proof, but it really means one proof here, one proof here, one proof here. Like every cell is going to have its own proof. And so, yeah, you have to basically do this computation for every blob of computing all the cells. Work like this. And the problem would have been that now this is in the critical path. So as you're trying to produce a block, you need to do this kind of heavy computation. And then, eventually, I mean, we didn't have this before, but actually what it looks like is that each column is going to come with proofs here. And this is how you actually check that you're getting the right sample. And instead, what it actually looks like in 7594, PeerDAS, is that basically the mempool structure is changed a bit from 4844. So what happens is, instead of gossiping just blobs, you're now gossiping blobs with all of the proofs already, and you're like verifying these proofs like already in the mempool. So somehow we're like moved verification from just here to like the whole system essentially. And this means that proof computation is now pushed to the transaction senders. So maybe this is a ZK sync node that's trying to send a blob transaction to the network. It needs to compute this cell when it's doing it. And so it is the only node that's actually doing this computation. So if you want to send a transaction that kind of requires this somewhat heavy cryptographic operation, you're the one that does it. Everyone else, from the mempool to everywhere else in the system, only has to verify it. And so in particular, it doesn't have to happen here. Also, the proposer only needs to verify it. It doesn't need to do it anything really heavy in the critical path. And then the last bit that we mentioned is you want to be able to do the initial distribution of columns fast enough. So this is this part, like in the initial distribution, like in the CL, once you're actually proposing a block. So again, this is the critical path of block building. So you want to be able to do this fast enough because, again, we have this tight timeline of a few seconds for all of this to happen. And more or less what it looks like is that each column should be sent to about 8 peers. It's like how the parameter of gossip in Ethereum. And so what you end up doing is that you end up basically sending about 16 times the data because there is this 2x erasure coding thing. And then besides that, you're also sending to kind of more than 1 peer at a time. And so sampling doesn't help here because other nodes are going to be sampling, but you as the proposer, you're originally the only one that has all of this data. And so you have to send all of it. You can't just send like a sample of it. And what this means in practice is that if you wanted to have 50 blobs, sending it all out in 1 second would require this much, like 800 megabits per second upload, which is not infeasible, but it's also not something that we normally think like a solo staker should have, for example. And so there's a worry there of like, okay, does this exclude certain actors from participating in block building? I think there's like a broader conversation about block building, but specifically right now in PeerDAS, the main solution for this is that, so first of all, we're mainly worried about local block building, not MEV boost kind of relays, professional builders, because as we said, the numbers before is something that if you really do this professionally, you can get a connection that's okay with being able to do this. But for a local block builder, which might have 50 megabits or even less, we would then assume that all the blobs that you're using to build are from the mempool. Like if you're building a block with your own node, you're not going to get private order flow or somehow the transaction that you're going to use to build your block are just going to be from your local mempool. So this assumption simplifies things a lot. And I mean, it's quite realistic for what we are actually worried about. And the way we use this is that basically, again, we can go back to our usual picture. The part that we're worried about is sending the data here. And we're saying, okay, all the data needs to be sent by this node because it's the node that has all the data. But actually before here, we have this whole part on the left where the data is already gossiped in the EL mempool. So actually this node is not, even though it's proposing this block with this kind of matrix associated to it, it's not the only node that has all the data. Like when it's getting the data here from it, somehow this is where the entry point of this data getting to this kind of block building unit. The data already exists. It's something that it's been obtained from the local mempool. So it already somehow exists in the local mempool and then presumably in other people's mempools as well. And so that's the thing that we essentially exploit. You basically send out the block, but you outsource the task of propagating the columns to other people that have these blobs in their mempool. So again, same picture as before, except the cells have been taken out, but they still exist in principle. And basically what happens is now, okay, you send out the block, people would receive the block, like for example, this node will receive the block, and then it kind of asks its EL node. So it again crosses this barrier of CL to EL. It basically does this call that's called get blobs, which is literally just asking this other node, do you have the blobs already? Like, do you happen to have like received them from the mempool? And well, in this case, this node does have all the blobs. So then this node, they kind of cross again the barrier of EL to CL. They get turned into this matrix and they get to the CL node, which then can do exactly the same thing that this proposer would have wanted to do, but maybe doesn't have enough bandwidth to do like successfully. And so it sends out basically these columns. And this is showing one node, but then it really could be like a bunch of nodes. So it could be that, some node is propagating this column, some node is propagating this column. This is why it's called distributed, because in principle, the data already kind of exist in the network. There's a bunch of nodes. All of the CL counterparts of these nodes already maybe have the data and they can contribute to this process. So it becomes a bit more of like a collaborative process in publishing the data. And even just this node doesn't need anyone's help. It already has all the data, so it can just immediately say, okay, I have it, before receiving it from anyone else. And this is kind of the last like challenge on the kind of current protocol and the block building side, which I think is the one that's really where sampling doesn't necessarily have all these benefits. And so you kind of really need to think a bit more carefully about all these like various problems. But I think for the kind of throughput that we're going to have with PeerDAS, then all of these are somewhat like okay solutions to all of these problems. And I mean, even for like future levels of throughput for the most part. But there are some limitations. And I mean, in one way you can think about them as limitations. In one way you can think about them as the next steps. Like what are basically, how do we evolve the protocol next to actually keep increasing the throughput? And one step I actually kind of mentioned already, we have this inefficient propagation on the CL. So we have this like redundancy of sending basically too much data around so that you end up having a lot of duplicates. And this is okay if it's things like attestations that are very small, but it's not okay when you're sending around blob data because it's a lot of data. And so you really want to be using bandwidth close to as efficiently as possible. And so there's a lot of possible things you can do. Could be more complex like erasure coding, but it can also be as simple as just doing a bit more pull, like a bit more of this like announce and pull thing that we do in the mempool and less of like pure just pushing the data. So basically biasing towards like bandwidth efficiency a bit, since like bandwidth is a limitation here, and or at least it would be a limitation at higher levels of throughput. And get blobs, this kind of process that we said kind of allows, helps with local block building, and with the system in general, as a bit of a problem that it needs all the blobs to be in the mempool. So for this to be useful, when you ask, do you have the blobs? You're supposed to get all of the blobs, not just some subset of them. And this is like, for technical reason, we don't have like too much time to explain. This has a few like negative consequences. But basically the solution is that it would be nice to have cell level messaging. So being able to really send messages at the granularity of a single cell instead of a full column, so that essentially even like a subset of things could still be useful and like useful piece of information that can be exchanged. This has a lot of benefits in general, this like cell level messaging thing. And it is really something that it's maybe like, I want to say the main thing that hopefully we can do next after, for the next iteration of this protocol. Then the mempool, I already said as well, is not sharded. So we do have this asymmetry where it's less important to shard the mempool than it is important to shard the CL. So do sampling in the CL. But still, eventually it is important as well to do it on the EL. And again, this together with cell level messaging is probably the second most important thing that's kind of on the plate right now for what to do next, essentially. And then there's something that's not really super related to PeerDAS specifically, but more broadly about scaling and just the way we use resources in the protocol today, which is that just the slot does not use resources very effectively. It's divided in these like 3 equal parts with like block propagation, attestation, and then attestation aggregation, or attestation aggregation and then propagation of the aggregates. And these parts don't really make too much sense anymore. And if you really want to try to use the time in the slot efficiently, this is not how you should do things. And somewhat, EPBS, hopefully in the next fork, is like a big step in trying to correct this. And so again, this is not unique to PeerDAS, but I think it's a general boost that's going to come in the future to Ethereum scaling in all kind of parts. And this, as I said, kind of 2 and 3 are really things to look out for in the next year. I think there will be like a lot to see like concretely about these 2 things. And hopefully all these limitations really point us towards what's the next step to increase the throughput. So I think there's really, even immediately after the Fusaka, there's supposed to be scheduled some BPOs, some blob parameter only forks to increase the throughput. I think, if I remember correctly, the last one is supposed to be for a target of 14 and a max of 21, which is a bit more than 2x from here. But after that, I think there's a lot of room in principle to observe what happens in the network, see that hopefully everything is fine. Actually, I think what we're going to see is that at least for full nodes, this is even going to make things much better than now, because we're not increasing the throughput nearly close to this like 8x kind of theoretical number that I said before. So actually it should reduce the bandwidth consumption a lot for full nodes specifically. So hopefully we can observe that everything is fine, maybe increase the throughput at some point a bit more with scheduling more of these like BPO forks. And then eventually we hopefully can have some of these like concrete improvements to push things like basically forward from there. And I think that's all I have.
Thanks for the presentation and for bringing clarity to what and why behind this proposal 7594. I love the graphical walkthrough of the process. That was really effective. And I also appreciate you having the recap of 4844 and KZZ proof. I'm sure these proposals are important to understand before we go ahead with proposal 7594. Thank you for sharing that.
My pleasure.
For anyone who are looking to maybe dive deeper, I would recommend checking out episode 104 with Terence and Potus on EIP 4844, as well as episode 96 with Dan Crad on KZZ Proof. We will try to add the links to description so people can follow that. Francesco, it was simply ingenious to apply erasure coding to cut data download requirement by 50%. I believe the change of mempool structure that you mentioned in the presentation was nice to have. And you also shared some challenges of the current process and possible improvements. I do hope to have some more questions around that to get more clarity about where we are and what we are looking at in the future. All right, I would like now go into the next round of question and answer, but I see some audience here. We do have a question from a guest. Kev is online, and Kev, if you would like to relay your question directly to Francesco.
Yep. Hello, Francesco. Nice to meet you.
Hello, stranger.
Out of those limitations that you mentioned, which one of those do you think would help PeerDAS the most?
Good question. I think probably either one or two. So I think one will make a huge difference, just kind of taking out this. I mean, basically, the gossip protocol is not built for gossiping a lot of data. And yeah, I think it's fine when you're not like pushing the limit of basically bandwidth that nodes can use. But once you start pushing against that, you really kind of hit a barrier there. So I think that would really make a big difference. And I think cell level messaging would also make like a really big difference, because I think it really would make the integration between the mempool and the CL part of things just work much better. It would it would really mean that we can rely on it much more. You can kind of see it from the comparison between the EL and CL side of things in that slide. It's somehow much better if you can just pull things from the mempool. There's a lot more throughput that you can push through the mempool, even without sharding, even without really tweaking the mempool too much. Then you can push through the CL. Of course, that differential will go down if you like improve how the CL works. But yeah, so, and I mean, in general, I think besides even this current higher level of inefficiency on the CL, I think like more generally we'll always kind of want to do as much as possible in advance, like out of the critical path with pre-propagation, rather than kind of having propagation be something that happens after block proposal. So yeah, I think cell level messaging is still like a really kind of key thing that unlocks a lot. Yeah, I would say those two. I think eventually we do want mempool sharding. I, at least personally, don't think it's as crucial as these other two things. But like, I mean, I think all three, it's probably something that it would be great to make progress on in the next year.
Right, that makes sense. I guess on the mempool part, is there a limit to the number of blobs that can be put in the mempool? Because the get blobs functions was assuming that all the ELs had all of the blobs, right? The relevant blobs.
Yeah. I mean, do you mean, is there like a de facto limit, or is there like an actual limit?
Yeah, I guess is there a practical limit? Like, can I just spam the EL with like...
Yeah, I mean, it's, well, like there isn't, I guess, there isn't like an in-protocol limit of any kind, and there isn't an allocation mechanism. Personally, I think eventually it would be good to have such a thing, like somehow allocate, like for regular transactions, not as important, but for blob transactions that consume like so many resources, and like we really have like quite finite resources to allocate, I think it would be good eventually to have like an explicit allocation mechanism, even for mempool throughput. But yeah, for the time being, there isn't, and really just relies more on like local rules of clients, and I mean, just like rate limiting, and of course, like there is like, you check for payments and like these kinds of things. But yeah, in principle, I think like sending a bunch of blobs through the mempool wouldn't be like the crazy expensive thing or something like that. So yeah, I do think there is a bit, that's one part of why it's a bit hard to like fully just go all in on this like pre-propagation and kind of relying on the mempool. I think we would all feel more comfortable doing so if it was more clear exactly like what is the behavior of the mempool, and if there were like clear kind of like guarantees, like properties around, okay, this is as much throughput as can go through the mempool, for example, because we explicitly allocate such throughput and we don't just leave it to sort of, whatever gets sent and then kind of clients just locally deciding what to do with it. But I think that's farther away, probably.
Right, that makes sense. I guess my last question is, like a couple of years ago, we did the KZG trusted setup for, and technically speaking, there was like 4 of them for different blob sizes. Do you think that will ever change like the blob size?
I mean, I think, yeah, eventually, like if you project far enough in the future, I think it most likely makes sense. But yeah, for like, as long as a blob still remains a sort of reasonable unit to be used by rollups, I don't know that there's like super clear benefits to switch into a higher size. I'm not entirely sure. I have to think about it a bit more.
That makes sense. Cool. Thank you very much.
Thank you, Kev. Francesco, my first question for you is about the real problem. Why is data availability the real bottleneck for rollups, and why can't they focus on computation?
Yeah, I think we're actually in a way maybe at a switching point, at least for the kinds of rollups that are on Ethereum, in the sense that I think for some of them, it might be that computation is going forward going to be the main bottleneck. And I think we're already like a bit seeing that. Like I think, I mean, for one thing, rollups that are on Ethereum since 4844 have essentially not had any time of congestion. Like there's been like brief times of the DA layer being congested, but for the most part, whatever barriers they've had on their scaling have been more like their own kind of barriers, like related to their chain and not on the DA layer. But yeah, until today, still, like if you look on L2 Beats now, the total throughput of the chains that are using the Ethereum DA layer is something like 250 transactions per second. And sure, transaction per second is not the greatest metric, but it tells you something. And yeah, so I think until this point, it's still something like 15 times more than the throughput of just Ethereum mainnet. So already like a lot has been achieved in terms of scaling in that sense. But until this point, still kind of working with like, it's not a scale that can support even a single chain that's hugely, that's with like thousands of transactions per second or something like that. So I think that's why it has been like at least perceived, even though the DA layer has not been congested, but still like I think the perception is until this point that you cannot really scale a chain too much by just relying on Ethereum DA. So in that sense, I think it has been the bottleneck, at least in like planning for the future. Like, can I actually take my chain to be like this scale and so on? Can I go and try to acquire like all these new users, or will I then eventually saturate the whole DA layer by myself and so on? And I think we're kind of moving away from that. Like I think PeerDAS really is like a pretty big step forward. I mean, it's not going to happen in one day. As I said, the initial scheduling is that the throughput will like a bit more than double for maybe I think in January is the last PPO. I mean, as the kind of tentative schedule that has been agreed on, I think very, very recently last week. And so at first it's not going to be a huge step all in one go, but it really sets the stage for then doing this consistently. So it's not meant to be like a 2x and then let's talk about it in 2 years. It's meant to be like this 2x is like the first step, and then there's kind of like meant to be some of these steps pretty regularly for at least some time. Of course, eventually there's no exponential growth forever. But yeah, so once you think about this in the context of already 4844 was a 3x, then Pectra has done another 2x, now we have another 2x, and we have a plan for how to keep doing this for some time. I think you really start to see that, okay, actually DA, at least for the chains that have been on Ethereum, that are using Ethereum DA, will not really be the main bottlenecks. And yeah, they'll have to turn to kind of their own like state management, computation and so on to actually be able to make use of the throughput that the DA layer gives them.
Yeah. You indeed mentioned in your presentation that this could be the first version of PeerDAS, and there are CL critical paths that can be improved in future. So we are just looking forward to what are other upcoming changes with respect to this particular proposal. Talking about engineering pain points, from a networking perspective, what was the hardest part of designing PeerDAS? Was it peer discovery, gossip routing, or proof verification?
I think depends who you ask. I mean, maybe if you ask Kev or someone that has actually worked on the cryptography, they might have a different answer. I actually sort of started working on this when most of the cryptography in a way had been done, because like the 4844 already existed, so a lot of the infrastructure was there. Of course, there was then like more to do for PeerDAS specifically, but like a lot of the foundations basically were actually made for 4844. So yeah, maybe not that part. But yeah, from purely networking, I think like generally things don't actually look in a way that different from 4844 if you squint enough. There's still these subnets, you still kind of send these like relatively big pieces of data in subnets, but introducing sampling, and so the fact that now all of a sudden not every node in the network is someone that you can actually get the data you care, that you can sort of, that's an interesting peer for you in terms of the sampling needs that you have. I think this is something that really was quite challenging. So yeah, basically peer management, I think more broadly, like figuring out, okay, I have this set of nodes and I needed to be able to cover my syncing needs and my sampling needs and so on. And I need to manage what they tell me. Like basically each node is telling you, okay, I care about this column, that column, and you somehow have to manage a peer set that allows you to also like satisfy your needs. essentially. So that, I think that part is something that like was a bit different from what came before and challenging.
That makes sense. Well, I'm trying to understand this. If PeerDAS is the answer for data availability scaling that we are doing with Ethereum, and you also mentioned that there could be some follow-up upgrades or follow-up EIPs. So what are the follow-up designs look like? Could that be multidimensional DAS or any other research that you would like people to start looking into?
Yeah, so I mean, historically, the somehow end goal of DAS was meant to be this like 2D construction, which does have a lot of nice benefits. But I think, at least the way I see it, I think PeerDAS kind of gives us a good foundation to keep improving on for quite some time. Like, I think there's a lot of relatively low-hanging fruits kind of improvements that we can make on the foundation of PeerDAS. And they're not really like deep redesigns or like huge protocol changes or something. It's more like tweaking certain parts of the protocol, building on certain things and improving them. So it's like some of the things that I mentioned, they're not necessarily, I mean, they're not in principle even necessarily things that you have to do a hard fork for. So I think for at least some time, it probably makes sense to try to just like push this to basically the maximum throughput that it can support, like really try to like squeeze as much as possible from this foundation that we have, instead of trying to like fully rethink like the whole design. And then, yeah, I mean, I think there's definitely space for constructions like 2D or other things farther in the future. Eventually, there's also the post-quantum question. So like at some point, there's definitely different kinds of considerations. But I think for quite some time, like I wouldn't be surprised if this is what it looks like in 3 years, still more or less with some like bells and whistles.
That is good to know. I have a question which is more based on the documentation part of this proposal. I understand when the proposal was initially documented, it was marked as a networking proposal. But now the category has shifted. I think it shifted recently on September 5th, so it's less than a month. So why was PeerDAS moved from networking to core? What was the trigger and why do you think that it is important to keep it in core category?
I have to say, I'm not really an EIP historian, so I don't know even like, yeah, I don't know exactly like what is the reason for. I think I remember Alex made this PR, so you'd probably be a better person to ask. But I assuming it's because, yes, in principle, you can think about it as is just some swapping a bit of the networking backend, but then it actually, from like a user's perspective, it looks the same as for EIP-74. There's just blobs and there's KZG commitments. So like you can think about it as just there's some backend thing that's mostly networking that you're swapping, but really it's more complicated than that. Like it's touching the mempool, it's changing the cryptography, it's definitely changing the networking, but it's changing lots of kind of objects everywhere. So I think core, probably because it more accurately reflects the fact that it is a huge change, is like, yeah, I think it's as big of a change as for EIP-44 itself. Somehow like it is an evolution of it, but like it's really a kind of an EIP that touches a lot of things and that really sets the stage for, in a way, like the next phase of this whole part of Ethereum, the data layer. So I don't know exactly what are why something should, like, what are the rules for classifying something core or networking or so on, but core does feel more appropriate given the scale of what the EIP is.
Well, whatever the reason may be, I'm very happy to see this proposal finally moving into core proposals, because I feel like this is the essence of the Fusaka upgrade, and having a proposal that has the most impact in others category didn't feel right to me. So I'm sure that there must be very technical reason to switch the categories, but I'm happy about it and happy to see it in core section now. Well, I have a few more questions for you. Those are kind of juicy questions. You can perhaps choose to answer in one word or maybe a few sentences, whatever feels okay to respond to those questions. So if PeerDAS makes Ethereum data availability layer dramatically cheaper, does that eliminate the economic incentive for alternative DA providers like Celasia or EigenDA?
I think there might always be some room for alternate DA providers, like even in a farther future. I mean, I think there definitely is some room now, because even with PeerDAS and even projecting, maybe 1 or 2 years in the future, it's still not gonna be able to satisfy like the demand for DA across like every possible chain. And I mean, yeah, this might just be a goal that isn't actually possible to satisfy whatever global demand for DA exists. Then whether or not Ethereum should care about this is a different question. It's unclear. I think it's very possible that you can have a DA layer that's large enough to satisfy most of the things that you might care about satisfying, and I'm sure there is some tail out there, but that you don't care about it. Or it might be that that's not even necessary. Yeah, it's not kind of important to somehow fulfill like all the even important DA or like relevant DA needs, let's say. So I think that's just, not a super clear thing yet.
But I think whether Ethereum cares or not is my next question. Just imagine that in future, Ethereum DA becomes extremely efficient. Do you see these projects competing less and coordinating more? Or will the DA pricing war get even more intense?
So I hope regardless of for a future where whichever, or at least like some amount of chains that are using Ethereum DA is settling on Ethereum, just generally being like in the kind of greater Ethereum as L2s or app chains or things like that. I hope that there is like at least some core of them that are more cooperating that have at least like lots of amount of shared activity and so on, like through mainnet, it would be even better. I don't think this is going to come automatically just by like, even if you somehow made DA free, I mean, which it almost is today. But yeah, even if you made it free for, somehow guaranteed that it was going to be free for a few years, I think there still is incentives. I mean, the cooperate or compete incentives, I feel like come from something else. Like there may be competing for the same users. And yeah, depending, I mean, they might sometimes have incentives to, cooperate or for example, try to build like interop infrastructure together or things like that, for other reasons, but I do think some element of competition is it's impossible to erase.
And maybe it is healthy as well. Some level of competition is generally healthy. All right, my next question is your honest answer or honest thought on, is Ethereum becoming too dependent on Rollup? What if layer 2 stops playing nice and optimize only for their own benefits?
Yeah, I mean, I think that's definitely a fair concern to have. And yeah, I personally think part of the answer to this is just making mainnet activity itself be or making mainnet itself attractive to certain kinds of activity, making mainnet itself be like more attractive like hub for liquidity, so that somehow, I mean, in this, it kind of ties back to this like cooperate versus compete that we were mentioning before. I think it is possible for mainnet to be a more interesting cooperation partner. And this kind of depends also on like the activity that happens on mainnet, whether or not there is liquidity, there is activity, there are users that are kind of based on mainnet, there are assets that are based on mainnet and things like that. So yeah, I think this really depends on like how healthy does this look like. If there are reasons for Rollup to kind of still be Rollups to be close to Ethereum, to talk to Ethereum, to interoperate. I mean, in this, I mean, not to people building on Ethereum necessarily, but just to the actual like dApps and so on, to use bridges and basically to interact with what's happening on Ethereum. Then I think they will. Like, I think the incentives will naturally be that if there's a lot going on Ethereum, then you're not going to ignore that, and they're not just going to use DA and be their own kind of island out there. So yeah, I think this really depends on basically what does mainnet activity look like, and can we kind of build this like network effect around it?
Yeah, and I definitely see a mutual growth of all the projects around like cooperating with each other, and we can take advantage of the tech explanation or tech exploration that is going on in different projects to make the ecosystem better. Unlikely to happen, but what if PeerDAS unperform? What's the plan B for scaling block throughput, if there is any?
I mean, I think that the general answer is that if there is anything that looks like a security problem, then, well, that's like priority number one for Ethereum. There's never any kind of scaling or any feature that comes before security, before aliveness, before like if, for example, you mentioned reconstruction, if it, for whatever reason, it turned out that there's too much data in order for reconstruction to happen timely, or and this caused the chain to have problems like skipping slots or somehow like losing liveness for some time or something, then I think the clear answer would be like taking a step back and undoing that, which might just look like reducing the blob throughput or something like that, which actually PPO's kind of blob parameter only forks kind of help doing in a bit easier way than if you had to do like a whole fork from scratch. But yeah, I personally don't think that's going to happen, because for two reasons. Like, one is just there's a huge amount of testing that goes on, like all these kinds of scenarios, reconstruction, and I mean a lot of other possible edge cases or just general system load that might happen have been tested, are being tested, and so on, and will be tested a lot more until mainnet. And partially because also the way that throughput will be increased is somewhat conservative in two ways. Both that the actual throughput numbers, I think, are fairly conservative, that the ones that are chosen, but also that it's going to be gradual. There's going to be the mainnet launch, which is not going to have any throughput increase. And there's going to be a BPO with a small increase, and then a second BPO with another small increase. So I think this like kind of graduality should enable us to kind of see if there's any degradation in behavior and then react if needed. And then, the final reason is also just, I think, of course, there's theory and there's code, but like on a theoretical level, I don't think we're putting some, a huge amount of new load on the protocol. Like I think the weaker participants are somehow the ones that you would be mostly worried about. Nodes that are running in data center or something like that, I really wouldn't worry. Like this is not some crazy amount of load, neither in terms of computation or in terms of bandwidth. And when it comes to the weaker nodes, that's exactly who the protocol in a way, like why this whole sampling thing exists. It's actually making, and given the throughput numbers that we're going to have at first, it's actually going to make things better for them. Like they're going to download less data than before. So yeah, this is more or less why, of course, it's a huge change. With every change comes, there can always be bugs. We're still talking about 5CL clients, 5EL clients, massive network. So everything can happen. But I think there's a lot of reason to be optimistic about things going well.
Right. And I think having BPO folks giving this ability to adjust the parameters independent of network upgrade that happens already gives us a lot of comfort. It was just an hypothetical question.
It's a very fair question.
Well, my last question for you is mostly inspired from the internet. People suggest that DAS may be the major step before Ethereum becomes the global data layer. What do you think? Is it real or is it a hype?
I don't really know what would global data layer mean, to be honest. I guess one interpretation could be just the data layer for all blockchain data. Yeah, I personally think it's unlikely to be the case. Again, I think it depends how you weight things. If you're just talking about pure data amount, then I think that's just impossible. There's always going to be all kinds of activity that just cannot exist on Ethereum. We do have constraints of, we want to have, normal nodes be able to participate in this. Sure, sampling helps, but it helps only up to a certain point. So I think there's always going to be activity that cannot exist on Ethereum, activity in a different way with kind of some economic weighting. And I think there's maybe a bit more hope. I think the optimistic case is that, any, maybe 90%, if you weigh it by actual value, so it could be fees or something like that, of activity might be on Ethereum. That might also be optimistic. I'm not sure. But yeah, I definitely don't think that purely looking at data, then this is a realistic thing to say all data is going to be on Ethereum. Someone playing, online chess on a blockchain is probably not going to be on Ethereum for the foreseeable future, I want to say.
Yeah, that makes sense. But thank you so much for providing an honest answer to this question. Well, this was pretty interesting deep dive. Thank you so much, Francesco, for sharing about PeerDAS. I believe this is one of the most discussed proposal for the Fusaka upgrade. Thanks for your time.
Thank you.
Dear listeners, if you enjoyed this episode, please like, share, subscribe, and tag us on Twitter. If you want us to cover any other specific EIP, please send us your recommendation and we will try to reach out authors to make it happen. Until next time, make the upgrade safe, make the chain safe, make users' transactions safe. Let's keep scaling Ethereum the right way. This is Pooja Ranjan signing off. Cheers, everyone.